Hello everyone, Aaron here and welcome back to Leetcode. Today's video is a little different. We're doing the min cost to connect all points problem, but as you can see I've already got a solution here. I did this one a while ago and I went to edit the video for it and well, we got there in the end, but as you can see it was not good. This is pretty rough. Never actually accomplished it in TypeScript. I had to switch to Python just because there were better libraries available for Python to fill in some of the pieces I needed rather than implementing them from scratch. Now, this resulted in, well, as you can see, the first submission was just after 5. The final submission was sometime after 7. Long story short, I had well over 2 hours of footage. Well, I struggled, to say the least. It'll yell at me if I'm wrong. Balls. Shoot. But when I was going through editing it, I realized I'd forgotten a very important data structure that I would need to solve this problem. So, I think what we do is basically redo this, but this time with the correct data structures in place. And the key one that I was forgetting about was what's called a disjoint set data structure. They're quite cool and they're very crucial when it comes to implementing what's called Kruskal's algorithm. So, stepping back a wee bit, let's go through this. Min cost to connect all points. You are given an array of points representing integer coordinates of some points on a 2D plane, where point I is a pair xi, yi. The cost of connecting 2 points xi, yi and xj, yj is the Manhattan distance between them. Xi minus xj plus yi minus yj, absolute value of each. We want to return the minimum cost to make all points connected. And this is a minimum spanning tree problem. So if we imagine all of these were already connected, we're trying to pick the connections that are just enough to let you get from any point to any other point, but is the cheapest possible way of doing it. It's a bit like if you are building train tracks and you don't want to give people convenient journeys, you just want to make sure they can have a journey. This is the way you would do it. So let's basically trash everything. I don't want any of this. What I want to do is basically have a go at Kruskal's algorithm. And the way Kruskal's algorithm works is we have let connected sets is equal to, well, empty disjoint. Let's call it a new disjoint set from points. And then what we want to do is while connected sets dot sets is greater than 1. In fact, let's do another thing here. We want let distances equal all distances points. Oh, we've got more than one connected set. So we would start with 1, 2, 3, 4, 5 connected sets because each set contains just a single element. And then as we add an edge, for example, these ones here, the number of sets is going to be 1, 2, 3, 4 sets because these two are now in one connected set. Then what we want to do is let edge equal distances dot shift. There's probably better ways to do that. In fact, no. Let's do it the better way. Let next equal 0. Let edge equal distances next distance. In fact, no. Well, edge equal null while edge is equal to null. Edge equals distances next distance. If so, an edge is good to take if it is connecting two different disjoint sets. But if, say, for example, these three were connected here and here, grabbing this edge is bad. We don't need to take it again. You can already get from here to here via here. You don't need a direct route. It's not minimum. If causes cycle edge connected sets, if selecting this edge would cause a connected set, we want to do edge equals null, and either way next distance plus equals 1. So we're going to check what number 0. If it's bad, well, then we're going to mark the edge as null and check the next one and keep doing until we've found one. Then what we want to do is we want to do connected sets edge. So if we have, say we end up with an edge that connects this group here with this group here, we basically want to turn them into one large group. One thing I'm assuming here is that these distances are sorted, so that we're always checking the next smallest distance to take. But we can do a sort. That's fine. That's a perfectly safe thing to do. So let's do all distances first. And we want to give back effectively, well, let's do let's make just another number array. But this one's going to be shaped rather differently. For let I equal 0, I is less than points dot length I plus plus. For let j equals 0, j is less than points dot length j plus plus. What we want to do is we want to compute the distance between them, which we will do in a second. And then what we want to do is we want to do distances dot push. I want to put on I, j, d, the distance between I and j. In fact, we don't need to start at j equals 0. We need to start at j as I plus 1. Because if we know the distance between I and j, we know the distance between j and I. Then at the end, what we want to do is distances dot sort. For I and j, we want to do I2 minus j2, just to get these things in order. Return distances. Now, distance here, we wanted to do math.abs plus math.abs, where it's points I 0 minus points j 0, points I 1 minus points j 1. So this is the difference between the x's and the difference between the y's. So this is our Manhattan distance here. We make sure we get them all in order such that, well, we're not interested in which ones are I and j, we're interested in their distance. We want to make sure the smallest distance comes at the front. So distances.sort, this is expecting the two values. So we can say, is I less than j? I is less than j. If this value is smaller than this value, we're going to get negative. Negative indicates smaller. It's a bit of a weird quirk, but go with it. We can't just use sort natively because, well, 1, it would be comparing these things, and 2, it's doing a string sort. So even if we just had the raw numbers, 10 would be less than 2, which is terrible. One of my many complaints about JavaScript. So now we want to do new function, new disjoint set based on points, which is number array. I don't actually care what the points are. All I care about is how many there are. N is points.length. So what I want to do is I want to do let sets is a new array of size n for let I equals 0, I is less than n, I plus plus, sets I equals I. Now basically what this says, the way a disjoint set works is every set is given a representative. So if item I has representative I, then it's in its set. But if item I has representative j, it's in the same set as element j. The idea is that you can kind of walk back up until you reach the item whose representative is itself. So you know you've found the representative. And basically the number of distinct representatives is the number of sets that are in your set of disjoint sets. But to begin with, we know that the number of sets is n. Let's call that count, in fact. So we have initially n sets, and the sets are these. So that's our new disjoint sets. We need to do a causes cycle. And this is based on an edge, which is a number array. Remember, this is our ij distance. And we also get our connected sets. And we want to return a Boolean. And the idea here is we find the representatives for I and for j. Edge 0, let j rep is the representative for in the connected sets for edge 1. If I rep, no, what we want to do is return I rep is equal to j rep, because if these are in the same set, they have the same representative, and therefore adding a new edge would cause a cycle. If they are in different sets, they will have different representatives, and therefore connecting them will just join those sets together, but it won't cause any problems. So representative of the connected sets element, which is a number, and it returns a number. And what we want to do is effectively, well, if we look in connected sets for element and find that its representative is itself, then we return that. If it's not itself, we want to find that element's representative until we finally find the point where the element is its own representative. So, in fact, no, that rep is equal to connected sets dot sets elt if rep equal to elt return rep, I guess. And then we want to do is, while true, we just want to repeat this procedure. Otherwise, because if that's not true, we want to set elt is equal to rep. So now we're looking for the representative of our representative. So one way to visualize this is as a tree. So if we're looking at, say, this element here, if it's its own representative, great. If it's not, we might find that its representative is this one here. And if that's its own representative, great. But if it's not, we might find, say, this one is. Now, this is its own representative, great. We are now done. And what that means is this one is sort of transitively connected to this one here, like in a tree structure. So we just sort of walk our way back up until we find the representative. Obviously, this is terrible if we've got no fixed point, but we'll assume we've not broken anything along the way. Then what we want to do is connect these things. We want to connect the connected sets with a new edge, which is the number array. What's that called? Unit, I think. And then, so to connect the two edges, the two sides, basically what we want to do is, well, very much like before, we want to find the representatives for each, and then basically connected sets dot sets I rep is J rep. So this says we want to join the two sets together. So if this was the representative for this set and this was the representative for this set, all we're going to say is, well, this thing is no longer its own representative, it is this. So we would now follow the chain up one step further to find this is the parent of everything on this side and on this side. So they're all now one big set. But we also need to be careful because the connected sets dot count is reduced by 1 because we have taken two sets and turned them into just one set. Now, one thing I've forgotten to do is keep track of the total distance. But that's easy enough to do given what we've already done. So the procedure for Kruskal's algorithm is quite trivially find the lowest cost edge that doesn't cause a cycle and use that edge. Keep going until everything is connected. If everything is connected, there's exactly one set of things that are connected. So we're going to keep doing that until we get there. Let edge is equal to null. Pick an edge that doesn't cause a cycle. And then connect the sets that it connects. Easy enough. It's just this machinations around building a disjoint set that is the real quirk. Let's test it. See how many horrible mistakes I've made. Find the unit. Maybe it is void. This is one of those things where each language has its own name for it. Great. Let's use all the test cases. Oops, that was a bit too quick. Excellent. Right, moment of truth. Let's submit it. Not super optimistic given the horrible track record. Hey! Okay. So this is one of those things where if you're not an absolute idiot and actually get things right, then you can solve the problem much more efficiently. Hopefully that will be much less of a mess than the travesty that was the previous version of this video. Thank you very much for watching. Do let me know if there's any other kind of videos you'd like me to do down in the comments. I'd love to hear from you, love to hear your ideas. That's all from me, and I will see you next week. Bye.